Hello, we're going to take a look at a couple AP questions right here involving limits and kind of graphically how to understand limits and the differentiability in regards to limits. The first one is a basic question of analyzing a graph and what does it mean for a limit to exist and how do you see that on a graph. The question asks, the function f is shown above. The line x equals 1 is a vertical asymptote. Which of the following about f is true? All right, well, let's go through the options and see if we can knock them off or say yes or no to each one. So the limit as x approaches 3. So remember, when you have to do the limit as x approaches 3, it has to be the same on both sides. The limit from the left has to equal the limit from the right. And also it's the limit, so it's what y value the graph is going towards, not where the function is defined. So for instance here, f of 3 is equal to 1 because it's filled in at that dot, but the limit does not exist. This is not true. It does not exist because as it approaches it from the left, it equals 3 because it's going up to 3. As it approaches it from the right, the graph is going towards the y value of 2. So 3 does not equal to 2. The limit from the left does not equal the limit from the right. Okay, let's take a look at B. Looks like we're still looking at x equals 3 and the limit. So as x approaches 3 from the left, well, there we see it approaches 3, like we said earlier. As it approaches 3 from the right, it approaches 2. So the question is 3 less than 2? No. Okay, so that's not true either. Okay, the limit as x approaches 4 does not exist. Well, in order for a limit to exist, it must be the same from the left and the right. And as we look at x approaching 4, nothing funky is happening here. It is just a basic old continuous function there. It's approaching the same value of 2.5. So does it not exist? No, that's false because it does exist. Well, it sure looks like D is our correct answer here. So let's check it out and hope we're right. That'll be great. All right, the limit as x approaches 0 from the right. Well, as it approaches 0 from the right, it equals 2. All right. What about the limit as x approaches 3 from the right? Oh, we already did this one. That also equals 2. So yes, in fact, they do equal each other, so our correct answer is D right there. All right, let's look at another problem where we analyze the graph and talk about limits. This one is saying, given f of x, as shown in the figure to the right, at which point is that function continuous but not differentiable? All right, so continuous, looking at the graph, the limit from the left equals the limit for the right. Or another way you can think of it, just are there any holes or breaks in the graph? Well, the only place that this is not continuous is right here at the vertical asymptote. Okay? Now, differentiable. Well, again, that's the limit of your difference quotient from the left must equal the limit of the difference quotient from the right. Or let's think about that easier. The slope on the left has to equal the slope on the right at a point. Well, first, let's knock out the points where it is continuous and differentiable. Okay, for example, A right here, continuous and differentiable. Nothing funky happening there either, so it's not A. C is another perfectly normal point. Okay, just continuous and differentiable there. Okay, and then moving on to D, that's a smooth little turn that it's got going on there, so that is continuous and differentiable. And then E is another smooth curve there, continuous and differentiable. We're left with B. In fact, that is where it's continuous and not differentiable. But why? Well, we call point B a cusp. There are 3 points where a function is continuous but not differentiable. 3 main things to look out for. You have the cusp, which often looks like at point B. You have the corner, which might look something like that, or like the absolute value like that. And then you have the vertical tangent. The vertical tangent is where the graph goes continuous, but at this point right here, it has a vertical tangent line, which there the slope is undefined. All right, why are these places continuous and not differentiable? Well, a cusp is defined as something where the slope on the left approaches positive infinity and the slope on the left approaches negative infinity. And that can be flip-flopped around. Negative infinity on the left, positive on the right. Okay, because for a function to be differentiable, the limit on the left has to equal the limit on the right. But here we're going to positive infinity and the negative infinity. Left and right are different. A corner is the same idea, except it uses finite numbers. So it's where the slope on the left is approaching something, and then the slope on the right is approaching something totally different. Maybe slope is 5, and then it abruptly changes to 2. Or in the absolute value, it's -1, and on the right side, it's 1. So the slope on the left and the right do not equal each other, but it's two finite numbers. And then a vertical tangent, because the other place it's not differentiable is if the derivative is undefined, or if there's like a 0 in the denominator. And if you think about the slope of this, well, the slope is rise, so like y2 minus y1 over run, x2 minus x1, but you know in a vertical line, that's 0 in the denominator, causing it to be undefined. Now that's the slope formula, which derivative is as the difference in x goes to 0. But in essence, that idea happens. You get a 0 in the denominator, which means the derivative is undefined, which is a place where it's not differentiable. So in this case, point B is a cusp, and therefore it is continuous, but it's not differentiable.